technology, which is really one of the wonder, I'll say, wonder of the semiconductor industry. And fortunately, I was in industry working during that time. 2013 is when I started working in SanDisk, and that is the time SanDisk decided to go from 2D to 3D transition. That's part of the 3D NAND technology development team, and we had a lot of innovation, a lot of patents as a company. Now it is more like a workhorse for industry, the 3D NAND, right? It is increasingly replacing hard disk drive in a data center, right? NAND storage is actually, 3D NAND is more like number of layers, right? In a three-dimensional building. More layers you can grow, you can have more bit density, right? So that is still not going to its end yet. It is still, I'll say, the middle phase of the technology development. Whereas hard disk drive, if you look at, DRAM, if you look at, right, their scaling has been saturating. But 3D NAND is keep going on every 2 years, almost like doubling the density. So that's interesting and very important as well. So today's class, I'll talk about the key process challenges to make this 3D NAND technology and what are the key innovation, okay? Okay, so now if you want to have more bits, right, what are the options you have? Suppose you want to pack more bits in a given area, right? One option is not a given area, okay, you can have bigger size wafer, so that's not a definitely good solution, but yeah, still, wafer size is increasing every 10 years. But this is one of the solutions that 2D NAND technology or 2D technology used to follow, shrinking the device dimension. Make your footprint of every cell small, right? So shrink in the X, shrink in the Y direction, right? Your gate length should be small, gate width should be small. So that's what 4X means 40 nanometer or 40 something nanometer. 3X means 32 nanometer or 30 something nanometer. 2X, 1X. So that's how the technology has been shrinking for two-dimensional NAND memory, which is very similar to your CMOS process, CMOS technology scaling, right? At what CMOS technology we are in right now? Around 5 nanometer, right? That's where TSMC makes. But 5 nanometer doesn't mean exactly the geometric dimension is 5. The geometric dimension is a little bit longer. But yeah, so that's the CMOS scaling, and that was 2D NAND also was following that. Other option you have is logically scale, right? Okay, I cannot make things smaller, but one cell can store multiple bits. So it's called logical scaling. So this is the physical scaling. You make things smaller so that in a given area or on a given wafer, you can pack more bits. Or another is, okay, my hardware remains same. I will logically scale. And if you recall, right, we had assignments and all, multi-level cell, where one cell will store 2 bits. Similarly, one cell can store 3 bits, 4 bits, depending on how many threshold voltage levels you can create, right? If you create 2 threshold voltage, high and low, you can store only 1 bit. But if you can store 4 threshold voltage, different threshold voltage, distinguishable threshold voltage, then you can store 2 bits per cell. With every threshold voltage level will represent 2 bits, right? Then if you can create 4, like here, 1, 2, 3, 4, you can store 2 bits per cell. So distribution is just to show you the statistics. So you, in a memory row, right, or in a memory word line, you will have thousands of cells. You target, okay, lowest threshold voltage should be, say, 0. But some cells can have a little bit high threshold voltage, some cells can have a little bit low threshold voltage. Okay, next threshold voltage should be, say, 2 volt. But some cells can have 1.5 volt, some cells can have 2.5 volt, right? So that's why you need to keep some gap between different threshold voltage levels, and that's how you can reliably detect which threshold voltage bin they are in. And accordingly, you can say this cell is storing 0, 1, or this cell is storing 1, 1. So 2 bits per cell. So that's the concept of logical scaling. And currently, if you buy a brand new SSD, or if you buy brand new thumb drive SD card, definitely it will be QLC, quad level cell, right? Or 4 bits per cell. That's why this industry is currently making it as its state of the art. Of course, if you want very highly reliable application, for example, NASA, if they want to send some SSD at the space, you definitely don't want to go for QLC, because QLC will have less reliability. Little bit of radiation goes through it, bits will be corrupted. But SLC will be more reliable because it has more gap between two states. It will be more faster to read and write, highly reliable. But why people don't use? Because people worry about cost, right? So SLC will be more expensive than QLC, and the storage industry is pretty much driven by cost. And that's why QLC, even though it is not reliable, even though it is a little bit slower, right? Still, or even though it has less lifetime, endurance is another important quantity for non-volatile memory. Everything is poor for QLC. Only good thing is less cost because highly dense. You pay cost per bit, right? So in cost per bit wise, QLC wins, and that's why this is the most popular technology right now. What else you can do? You can logically scale, you can physically scale. What else you can do to increase your bit density? So that's why the topic is 3D NAND. You can make taller. Tall is the new small now, right? So for example, earlier you can make small, you can have more bits. Now you make more tall. That is effectively, you are packing more bits, because at the end, as a user, we care about footprint. So if you have a tall building, then every floor is your bits that you can pack, right? So for a given footprint, you increase bit density by making things taller or by monolithically growing, right? These are not like you have one wafer, you have another wafer, you put them together. No, this is not the case. You have only one wafer. You pay price as a wafer, and on that wafer you make these multi-storied stacks for memory layer. Okay, so you're growing more and more memory layers on a given wafer, and that's how your cost is not increasing with more number of layers, right? You can increase your bit density. Your silicon wafer is same, which is in the bottom. So we'll talk about this technology a little bit more detail today's class. Okay, so if I want to summarize the whole 3D NAND or whole flash memory evolution, so you can say, yes, it was invented, if you recall, when you talked about flash, right? It was invented in Bell Labs by SMZ and Kang, I guess. So they first demonstrated floating gate memory cell as a non-volatile memory. After that, it was launched into market in 1980s, right? Predominantly by Intel and then Toshiba for NAND technology. Intel started NOR and then Toshiba started NAND. And then it was this geometrical scaling was going on for 20 years, right? So how to make things small and you can pack more bits. So that was the 2D NAND era. So your NAND cell are sitting on the silicon wafer. That's the 2D NAND, right? Your cell transistors are sitting on the wafer. And you have the, but if you make things smaller, the problems are your number of electrons per cell will become very, very small, because number of electrons per cell depends on the gate area or capacitance, right? Q equal to CV. If your capacitance is small, your charge is also small for a given voltage. Okay, so as you make things smaller, your number of electrons per cell becomes very, very small, so that it becomes less reliable, because one electron getting leaked will cause you significant drop in threshold voltage, right? One electron will have significant effect, right? Suppose you're storing 1,000 electrons for 1 volt. Then one electron goes here and there, doesn't cost too much, maybe 1 millivolt change. But if you're storing 10 electrons for 1 volt, one electron goes away, you're straight away losing 100 millivolt, right? So that's the difference. And then that's where this transition happened from 2D to 3D, because scaling further, 2D was near impossible because of all those reliability concerns. Right? It was susceptible to noise, a little bit electron trapping, detrapping will cause a lot of threshold voltage fluctuation. So you can have errors, right? So then the industry transition to 3D. So this is what the 2D array look like. This is what the 3D array looks like. These are red lines are the bit lines. These green layers are the word lines. So in any memory array, right, you have bit lines and word lines. It's typically grid. Word lines are the row, bit lines are the columns. So in 3D, it literally became the column, because this is one bit line will connect to a column, right? And I'll show a little bit more. And 3D cell structure was very different than 2D cell structure. 2D cell structure was like a MOSFET, planar MOSFET. But in 3D, it was more like a gate all around MOSFET. Okay, your channel is now vertical. In 2D, channel was sitting on the wafer. channel is where electron flows, right? It was on the silicon wafer. Now in 3D, channel is now vertical and wafer is sitting just at the bottom. So we'll talk a little bit more, but when 3D started, it started with 32 layers, 64 layers. When I was working in industry, the first generation was 32 layers, 64 layer we made, and then I quit industry and joined academia. But now industry is keep going, right? It is increasing more and more layer every 2 years. Currently 300 layers are still in the commercialized, right? 232 layer you can buy in SSDs. 300 layer is just commercialized this year. So maybe next year if you buy an SSD, you will buy a 3D NAND with more than 300 monolithic layer. This is the key, right? Monolithic layer. That means you're not increasing the cost. Cost is wafer, silicon wafer. On top of that, you are monolithically growing in a same process this many layers. Prediction is there can be more than 1,000 layer in near future. And this is a very good paper. Many of this content that I will teach today's class is taken from this paper. It talks about future perspective or for this 3D NAND. Okay, and I also talked about this is not just geometrical scaling happening. There is also a logical scaling happening, which is the number of bits per cell. For 2D, because the number of electrons was few, cell was small, right? It was impossible to make 4 bit per cell. 2D memory or 2D NAND, maximum they can go 3 bits per cell. There was no product for 2D NAND with 4 bits per cell. But because 3D cells are not big, because you can afford to have a little bit bigger dimension. Your gate is all around, right? So your cell area is large. You can pack more electrons, right? Yes?
So increasing the layer, the number of layers on the wafer, does that mean the wafer itself has to be bigger for that to work? Or
No. So silicon wafer is silicon substrate, right? So this extra growth is not crystalline silicon. This is polysilicon.
They just grow the
Yeah. It's like a pancake.
But is the layer bigger there as a result?
Yes. Overall, your memory will be, so earlier case, it was maybe 1 micron. Now it will be 10 micron. But as a user, right, we don't care. Versus 1 micron, 10 micron, we don't feel anything. But yeah, you are right. Your actual thing, right, where memory is sitting, it will be thicker. Yeah. But you are paying price mostly for the crystalline silicon substrate, which is remains same. Yeah. Okay, so this is the, yes.
Is there any problem with like power dissipation being like multiple layers on top of each other?
Yes, little bit, not significantly different power dissipation wise, because you have wider plate word line, right? So like earlier word line was line, 2D, but now in 3D, your word lines are plate. So capacitance will be a little bit large. So you may increase a little bit of power, but you are increasing also bit density. So per bit, power remains pretty much same. Okay, so this is the logical scaling, 3-bit, 4-bit and all, right? So higher the bit density. So this way, if you increase the bit density, you'll lose reliability or you'll degrade reliability. But this way, when people went from, so this way reliability was degrading, but there is a jump, 3D NAND, reliability again improved. Because now cells are a little bit bigger. You can afford to have bigger cell because you are now increasing bit density by making things tall. Right? So your area can be, XY plane can be a little bit bigger. So that's why reliability was better actually in 3D. Of course, as you go from one generation to another generation in 3D, your reliability is getting hit. And that's why industry is looking for newer innovations. And that's why I'll touch upon in today's class. Okay, so this was the first commercial 3D NAND chip that was launched by Samsung. Samsung was the first, even though the proposal was made by Toshiba in 2007 in a conference that, okay, we can make 3D or you can increase bit density through 3-dimensional scaling. That idea came from Toshiba, but silently Samsung made the product, launched it in 2024, so it's 2014, right? I joined industry in 2013. When 2014, Samsung launched the product, it was like all hands on deck in SanDisk that, okay, if we cannot make this technology in 1 or 2 years, we'll be out of business because 3D was cheaper, right? You can have much higher bit density with higher reliability. So that's why 2D NAND died after that, and really in 2 years, SanDisk also launched in 2015 or 2016, I think, as the first generation of 3D NAND. Okay, yeah, and these are the key papers. You can see first paper was from Toshiba, saying that, okay, we can go vertical direction, vertical array with 3D NAND. But yeah, research paper is one thing and product is different thing. So Samsung was the first, right, to launch the product. So, and this was their paper. And after that, there is multiple players like Micron, SK Hynix, they all chimed in, and there are different versions of 3D NAND. Okay, so let's look at how 3D NAND is fabricated, because it is very different than your normal CMOS process. So this is the three-dimensional view, right? You deposit first layers, like a pancake. You make pancakes on top of each other. So these green layers are metal word line. It can be polysilicon, highly doped polysilicon layer, or it can be tungsten, something like that, right? So first you deposit polysilicon, and then you deposit oxide, just like this. So layer by layer deposition, chemical vapor deposition can be a process. This is the first step. So you made your three-dimensional structure where you have multiple word line, right? And they're not shorting because you have in between oxide, silicon dioxide or thick oxide. Next step is the most difficult step. You punch hole or you drill hole along this stack. That will be your channel actually, right? Your channel will be, so in the top there will be bit line and the ground will be substrate. So in between you are punching hole, okay? So that is the most difficult process, and this is done through reactive ion etching. So you have a mask through which reactive ion will go in, and it will etch through this vertical layer, or like this. You embed those ions, right, through a mask, and that mask will etch away that area. So you're creating a cylindrical space through this stack, right? And those gaps you can see, right, hopefully on this slide. So those are the hole that you're etching. What are the dimension? Because if you know the dimension, then you will understand how difficult it is to make. Because this whole diameter will be, say, 80 nanometer. This small hole, nanometer, 80 nanometer. And height for one layer is also, say, 40 plus 40. 40 is for this word line. The green 40 is for this oxide. So overall 80. So now suppose you want to grow 100 layers, right? So then your aspect ratio, right, height is to width, is very, very 100 is to 1, for example. So you have to go so much deep, and you are assuming, or you want to ensure that every layer has diameter around 80 nanometer. So that's the most difficult challenge right now. Like in normal CMOS process, what is the most difficult or critical step? When you want to make things smaller, right? Lithography, photolithography. Like right now, extreme UV lithography. That is the most critical step. You want to make things smaller. But when you want to grow things taller, this high aspect ratio is the most critical step. That's where Lam Research, Applied Materials, those are the companies come in. They come the tool. They make those tools to make sure that you can do etching in such a high aspect ratio. Okay, so that's the challenge. You can see high aspect ratio process is the challenge, which will prevent maybe 1,000 layer. Because if you increase more number of layers, your aspect ratio will going to worsen, because diameter remains fixed. Diameter for each cell will remain pretty much same, say 100 or 80 nanometer, but the height will increase. Okay, so what is the last step? Last step, after you created that hole, you will deposit polysilicon, and I think that's what I think you are asking, right? So polysilicon will be deposited. It is not like you are starting with a crystalline wafer. Crystalline wafer is the most costliest thing. It's high pure crystalline silicon wafer, which is sitting in the bottom, which is the yellow layer you can see. But on top of that, you are growing those metal oxide layers. You are etching, and then you will deposit all those polysilicon and oxide layer. So this is your gate stack. Your channel is now vertical, right? And the cross section of this green layer and the memory hole, that is defining your one cell. So this is your one cell from, say, word line 1. This is another cell from word line 2, another cell for word line 3. So these are all the cells sharing the same channel or sharing the same memory hole. So that's the architecture. Okay, so if you want to know a little bit more, these are the few papers, one from our group, another from the earlier paper, the first paper actually, this is the one, 2007 paper, you can take a look. But the key process in this is reactive ion etching, which is the high aspect ratio etching, and that is the real bottleneck for higher scalability, right? Suppose you want to make 200 layers, suppose you want to know 300 layers, this aspect ratio will get worse and worse. Because when you push those ions, right, they will be less and less efficient as they go down, and you may not etch it. So you can see already there is a tapering. So this is not a mistaken diagram. This is carefully drawn. When you etch, right, in the top layer where ion comes in, they will etch more, a little bit more. So diameter will be a little bit wider over the top, say 80 on the top. As you go down, it will be 40, 60, 40 like this. If diameter is too small or if it cannot etch it, you don't have a cell over there. So layer to layer variation is significant in 3D NAND. And after that, you have to deposit all those gate stack, right? So you remember in a flash cell, you have a blocking oxide, you have a floating gate, you have a tunnel oxide. All those layers are those color coded here. So you'll be depositing them one by one. And finally, you will deposit the polysilicon. These are all CVD process, chemical vapor process, right? So that's the process. Any question on the process? How 3D NAND fabrication is done? Okay, so that's pretty much, I think sooner or later DRAM will follow the same process, other memories will follow the same process, because that gives you another dimension to scale, or another dimension to extract money, to make money, right? Because that's how you can increase the bit density. Okay, so now this is a closer look of your 3D NAND memory block. These vertical pillars that you are seeing, these are the polysilicon channel, silicon channel. Those green plates that you are seeing, these are word lines, right? So on a given, when you say one row, this is actually this row, this green plate. And all these bits will give you in that word line how many cells are connected in a row. And then there is a bit line on the top and ground on the bottom, which is the substrate. Okay, so this is the definition, and on the top layer is called select gate, and the bottom layer is called the select gate source, select gate drain. And we talked about it, right? Select gate on, off. That's how you select a particular block. So you have so many blocks together, parallel. You want to select a particular block, you turn on those select gates, and then you can read and write in that block. And if you take a closer look, just one column, this is how your one column looks like, right? So this yellow pillar is your polysilicon. These green plates, here we are showing as a circle here, disk. These are actually word line. So basically your one cell is a gate all around cell. Channel is yellow polysilicon, and all around there is a gate, which is a metal gate. And this is how your one string will look like. You remember when you talked about flash, we showed NAND array. So this one string will have multiple of this particular string, and that's how they will form an array, right? Top of this string is one bit line. These are all word line, which are metal plate, green layer. Every transistor will have control gate as the word line, which is the green layer here. Okay, so the bottom is the lower layer, is the bottommost layer, right? This is the bottommost layer, and then as you go on the top, the number of layers are increasing. Okay, so how many word lines are in a block is defined by how many layers you can grow, because this is one block. If you have 100 layers, then your one block will have 100 word line. If you have 200 layers, that means one block will have 200 word line. That's how it is. That means with time or with scaling, your block size will increase. Yes?
You count the select gate, and do you count the select gates when you're...
No, select gates are not for storing memory. They are just selecting, right? So your memory layers are the other one. Select gates are typically large and big, but memory layers are thin. Yeah. Okay, the one key distinction is we have polysilicon. We cannot have crystalline silicon in 3D. Why? Why we cannot have crystalline silicon in 3D?
The vapor deposition?
Yes, process, right? Crystalline silicon is done. You know how it is done? 1000 degrees centigrade in gold, right? You make a more like a cylinder, then cut it. You heat the silicon at a very high temperature, like 1000 degrees centigrade, and that's why it is costlier. Because when you want to make it crystalline, right, you have to change the crystal structure. So that requires very high energy intensive process, right? So you make a crystalline in gold like this, and then you sell it by cutting in wafer. That's why wafer looks circle. So that is a crystalline silicon process. You cannot do it here because the moment you go 1000 degrees centigrade, everything will be messed out, right? All your layers will be melted together. So your here temperature is critical. So 200 degrees centigrade, you cannot have crystalline silicon. You can make vapor of silicon, you can grow them layer by layer, and that's why the quality of silicon is poor. Because crystalline silicon will have high mobility, good quality, right? But polysilicon will have less mobility. So your sensing current will be limited, low. So those are the issues in 3D NAND. Anything else? Yes.
So basically, the silicon layer, typically it's like a pure silicon.
Yeah.
But it's because of 3D NAND, it has to grow it.
Yeah.
It's not as pure.
Yeah. So you are limited by the process. Yeah. Yes, definitely. As from a device physics point of view, we want crystalline silicon, but the process doesn't allow that. Yeah. So that's the limitation, and that's where the challenge came, right? So at the beginning, when I was working on this technology, I thought it may not work at all. One is you see so many holes. One hole can touch with each other, right? They are very closely packed holes. A lot of yield issue. We faced that when we are working in the industry. 60%, 50% was the yield. But in a memory industry, you need very high yield, right? 80, 90% yield. Yield means, okay, you are on a process, you are making 100 chips, 100 die. Out of 100 die, at least 90 die should be functional. You should be able to sell it. But because of the structure and all, 50% dies we used to reject because of short, because of a lot of process non-uniformity. But industry has solved all these issues, right? Right now, all the major companies, Micron, SanDisk, Toshiba, SK Hynix, Samsung, everyone is 3D. Nobody is developing any more 2D. 2D is over. 2D era is over. It is only the legacy technologies available. Okay. So this is your block structure will look like, and if you take slice, like cutting cake, for example. So this will be one block. This will be another block because one block will have sharing the same. The bit lines are common. Bit lines are global lines, right? Across the block, they will be the same. So that's why they are big, gigantic lines. Capacitance is huge. And when you talked about DRAM, we saw, right? DRAM bit lines are huge. So bit lines are it's a copper line, thick. It will be global for a given plane of the memory. Now, the cross section of this plate, right, will give you one block, or in more specifically, they call it sub-block, right? So you will have multiple sub-blocks will form one block. But yeah, sub-block or this cross-section of one plane, cutting it, will give you an equivalent 2D NAND, right? Because you are cutting it, one slice, then you look like a diagram like this, which is a 2D NAND diagram, where these green plates are the word lines, which I'm showing it here. It's one word line will form one page of memory, one row of memory. You read and write page by page, but you erase in a block wise, right? So if you want to visualize the same thing in 3D, this is how you can visualize it. Okay, this is one global bit line. You take a cut, you get this diagram. Can anyone guess how many bit lines will be there in a block? Guess? Or in other words, what is the page size? Page size in NAND is in the order of 16 kilobyte. So that many bits will be there, or that many bit lines will be there, right? So because every bit is connected to one distinct bit line. So if the page size, that means in a page how many bits are there, is around 16 kilobyte. So then 16 kilobytes of bits are there, right? You can connect them. Yes?
How many sub-blocks are there per?
That's a good question, and I'll talk about it, why sub-block concept is important for 3D. It was not there for 2D. 2D, this was your block. But in 3D, you group some sub-blocks to form a block. And there is a reason for it. Typically 4 sub-block per block. There are 4, or some company uses 6 sub-block for a block. I'll come to this point. Now let's look at how industry is thinking, because this is demonstrated. When I was working in 2016, 17, that time industry launched the product. but there is still 10 years. So in those 10 years, what are the innovation took place? So I just summarized in this slide, because from industry point of view, or from memory industry point of view, scaling is the most important thing. Scaling means increasing bits per footprint, or per square inch, per millimeter square. That is the real driving force for any semiconductor industry, right? Scaling. So what are the scaling direction? One is, okay, you can squeeze thing down, right? Because we talked about high aspect ratio is limiting you, right, from growing more layer. Suppose your instrument, your tools can etch 100:1. You cannot go beyond that. What knob you can play? Okay, I can make my word lines thinner. Instead of 80 nanometer being the thickness, I'll make 20 plus 20, 40 nanometer, right? If I make every word line or every plate thinner, then like this, then I can grow instead of 100 layers. I'm sorry, I think it's my phone or anybody's, I don't know. Yeah, so if you make things every layer thin, you can grow more number of layers. Instead of 100 layers, you can grow 200 layers. That's one direction, which we call vertical Z, right? Z is the Z axis, or vertical scaling, where you will scale the pitch. Pitch means the distance between two word line, center of one word line versus center of another word line. So that pitch, if you scale, you can grow more layer, because your 100:1 says aspect ratio will be maintained. Another technique the industry is now taking, which is very interesting, is like they are going into multiple deck or multiple tier. So this is your, suppose 100:1. You grow 100 layers, and then you make an interface in between, and then again you start growing, right? It's called multi-tier processing. You finish one DAC where it's 100 layers are grown, and you can see there is a shape, tapering shape, and then the same process will be repeated over there. Only thing is your thermal budget will be a little bit limited for the top tier. Yes, question?
In this case, is there a silicon substrate?
Yeah, silicon substrate is not only in the bottom. There is no silicon substrate in between. No. Yeah. But there will be some interface, few dummy layers. You don't use those layers because there will be a lot of process in non-uniformity at the interface. But yeah, you again grow this, and that will increase the cost, because at the end process time, right, will be repeated. You takes a couple of hours to grow this, and then same hours you have to use to grow that. That is, the process time will be higher, and more than that, fundamentally your temperature budget will be limited. You can grow the bottom layer with higher temperature budget, for example, say 300 degrees centigrade. But now when you grow the next layer, you don't want to distort what is already done. Right? Underneath you have tier 1, which should not be distorting because of growth of next layer. So those kind of challenges are there, but this is one direction industry is taking to make it 300 layer right now. The other is they're also squeezing XY, which is like traditional. So your diameter of each cell is not 80 nanometer. It is getting smaller, like 60 and 40 in that direction, right? So this will allow you to pack more bits in a given slit or in a given area. Third dimension is called architectural scaling. So in a memory array, this is your memory array, right? Your memory cells. But you also need a lot of CMOS circuitry as a decoder, row decoder, column decoder, charge pump, right? In Flash, it operates at a high voltage. That means from the external world, you can give 3 volt. But internally, those 3 volt has to be amplified to 15 volt. Because unless you raise the voltage, you cannot write or you cannot erase. So those CMOS area is shown with gray color, and the cell area is shown with blue color. In a typical chip, right? When I was working in SanDisk, for example, we had this structure. Your cell area used to occupy 80% of the die, and 20% of the die area used to be CMOS. Because your CMOS, right, or silicon is at the bottom. Your CMOS circuitry has to be made on the silicon wafer. Right? So that's why this is the CMOS. But next, the innovation came. Okay, this 20% area, can I minimize? Yes, you can grow this CMOS underneath the array. So this is the next innovation came, CMOS under array. This is CMOS near array. CMOS is your peripheral circuitry, which are consisting of sense amplifier, right? Your sense. It consists of charge pump, which consists of decoder, those circuitry. They put it underneath the array so that if you look at from the bottom, you don't see CMOS, right? Because they are hiding under the array. So you increase your area efficiency. You increase the bit density. And very recently, they started something called CMOS bonded array. So this is a little bit costlier process, but this gives you a lot of advantage. Why? Because when you do this CMOS under array, your thermal budget is very much limited. Because you have to finish CMOS first, and then on top of that, you grow memory array, right? Everything you focus on the memory array. So that's why your CMOS quality becomes very, very poor, right? Because when you are growing this cell, your CMOS circuitry starts to degrade. In a process, right? High temperature process, chemical etching, a lot of things happen. If you do CMOS bonded array, you basically take 2 wafer. So your cost doubles. You have 1 wafer just for making CMOS, another wafer just to grow memory array. And then you do a wire bonding. But this gives you a lot of advantage. You can have higher temperature budget for growing this cell, which is your main thing, right? Earlier you were limited, right? That my CMOS circuit will be degraded. I cannot go more than 200 or 300 degrees centigrade. But now, for cell, you can go for a little bit high temperature. Now maybe you can think about even crystallizing this cell. There are some proposals I do see in the conferences. It's mine, looks like. Yeah, let's see. Yeah, I muted myself. Okay, so now if you can decouple CMOS and memory array, then you can reserve more temperature for reserve more temperature for both CMOS as well as for memory array. So now there are a lot of proposals that can I make crystalline silicon channel instead of polysilicon, right? So there are some metal-induced crystallization process is there, MILC, right? Milk process. So those are the new direction. And the last one is the logical scaling. It happened. Right now, industry use QLC, which was never possible with 2D NAND. And there is a lot of papers talking about PLC. Even I saw this last week, I was in a conference, they showed 7-bit per cell is also possible. So a huge, making it so closely spaced, right? So these are the ways industry is moving on to increase the bit density. I think I need to speed up a little bit more. So I'll go one by one of those challenges. So this is the Z pitch scaling I was talking about. Basically, you are squeezing things down. Challenge here is, okay, yes, process-wise, it looks good. That, okay, you can make things thinner. Earlier it was 80 nanometer, now you make 40 nanometer, every layer is half. Then you can have aspect ratio 50:1, so that means I can grow more layers. But issue is cell-to-cell interference, right? When you write on one word line, because the other word line is so close, it will cause interference effects. Right? Then you can have a breakdown issue, right? Because you apply high voltages on those word line. So if you have high voltages, say 20 volt here, 0 volt here, then there's a huge stress on these oxides. They will break. And also you have word line resistance will increase. Well, word line resistance depends on how thick they are. If they are very, very thin, right, current will flow with a high resistance. What is the problem with high word line resistance? From a memory point of view, which parameter will affect you? Time, yes. With RC time, right? Because you will be giving voltage one end of the word line. That signal has to go all the way to the other end. And all the way other end is 16 kilobyte. It's a long, it is micrometer, but in a signal propagation time wise, it is large. RC delay will be very, very large. So yes, your read and write time will be longer if RC delay increases. So those are the challenges to make it thin. But yeah, industry is still going on. So when they made, so here in this plot, what I'm doing is the pitch, word line pitch on the here, and x-axis is the number of layers, which means different technology nodes. So this is generation 1, having only say 32 layers, generation 2, 64 layer, generation 3, 96 layer. So every 2 years, industry launch new product, right? New technology. So, and then you can find it out, what is the gate pitch in that technology, right? Number of layers is public, gate pitch, people can do cross-sectional analysis. And it is clear that the gate pitch is reducing, and it is almost now, it started with 80, right, as I said earlier, but now it is all the way to around 40. Now it is saturating. It's very, very hard to squeeze further because of all those challenges. Other approach, as I said, is the dual DAC, right? You have one DAC, and after you finish up this DAC, you go to the next DAC. So that's another direction of increasing more number of layers, because increasing more number of layers is the main direction right now for this industry. So this is the cartoon. You can see it's more like ice cream cone, right? One top of another. You get wider area in the top. As you go down, things become narrower because of inefficiency in etching. So this is what this number of subblock question you asked, right? So, so if you pack more number of bits in the XY direction, right? So this was Y direction, Z, vertical, and this is XY, right? So in XY, if you can pack more number of bits together, then you can have more density, areal density from the top. So now here, right, from one block to another block, you have to have a slit. So this is the slit will separate physically from one block to another block. So this block will have two groups of SGD. That means this is one subblock, this is another subblock. So you group them together, right? So if you want to save this slit area, right, because every inch, so every nanometer here is money, right? So this slit is doing nothing. It is a wastage area. Suppose if you want to remove this slit, then what you can do, you can increase the number of subblock per block. So for example, in this case, every block is having 2 subblock. In this case, every block is having 3 subblock. In this case, 4 subblock. Right now, maybe 6 subblock. So that's another way of increasing bit density, that you have minimal number of slit. Slit is a dead zone, right? To separate, physically separate one block to another block. So that's the, you can see 9 pillar. How you can 9, you can count it actually. So you can see 1, 2, 3, 4, 5, 6, 7, 8, and in between 9. So this is the 9 pillar in a block. This is, you can 14, right? So this is 19 pillars. So that's how you can increase bit density with XY scaling. And this is the percentage wise, how much area benefit you get. Third is this architectural scaling. Architecture means array versus CMOS periphery. So this was the traditional one. All 2D NAND was like this, because there is, in 2D you cannot have array underneath, right? Because your cells are sitting on the silicon substrate. So this is your silicon substrate. On top of that you have array, which is the layers. And then CMOS is in blue, CMOS circuits, decoder, charge pump, sense amplifier, those circuits. Then the next version, they put this array underneath. So your substrate, so this is the process, right? You start with substrate, you grow the CMOS, and then you grow the memory array. So that means CMOS will see most highest degradation. Whatever you grow at the end will be the good quality, right? So that's why CMOS was very poor. CMOS poor means charge pump, right, will require more time, more energy to raise the voltage. So that's why the industry came up with this hybrid bonding technique, that you have 2 substrate. You grow your CMOS separately on a different way for different process, totally decoupled. And after you make both these things, right, on one substrate, memory array, another substrate, the CMOS, you bond them together. But there is a lot of advancement in wire bonding techniques, right? Like packaging, advanced packaging. So this is what they do. They take 2 wafer. Your cost is pretty much double, and that's why industry delayed this technique. It is not like they did not have expertise. They had the expertise, but the market was not ready, right? You cannot have sudden jump in cost. So as far as you can go with keeping your process same, right? Scaling wise, they'll go. So from 64 layer, they all the way came to 232 layer up to this point. From 300 layers, what I know right now, that they are going in this process because it's becoming increasingly hard. Questions, comments, anything? Okay, so this is your architectural scaling. So all these things are happening, and that's how 300 layers is possible so far. And maybe in a couple of years, it can go to 500 or 1,000. The next thing I would like to say, there are two possible versions, and this is also driven by process. So you can have charge trap as the storage layer. So far in this course, we talked about floating gate, but floating gate means your storage layer is isolated, right? So like this here. This is green island. This is your floating gate where electrons will be stored. One floating gate is disconnected from another floating gate, right? You have a blocking oxide in between. So that was the process. But here you can see the scaling issue because this opening that you are creating, right? That is only for silicon. You have to make this floating gate outside this, the way floating gate is done. But much simpler process is this one, charge trap 3D NAND, where you make a bigger opening. That means aspect ratio has been relaxed, right? You make this hole diameter wider, and then inside this diameter, you first grow the charge trap layer. The problem here is your charge trap layer will be continuous. If you make floating gate like this, so here this green thing is floating gate. Here this purple continuous line is charge trap layer. So question to you, can I make floating gate also like this? Continuous floating gate. What will be the problem if I make continuous floating gate? Yeah, charge will leave, right? Floating gate means metal or metallic. So that means everywhere charge will be same. That means I cannot make this is erased, this is program. Because program means lot of electrons. Erase means no electrons. If I make them continuous like this, now here how does it work? Because this charge trap is a nitride layer. It's a localized trapping, right? It's more like an insulator. So that's why this material change, silicon nitride instead of polysilicon. Polysilicon is used in floating gate. Okay, so if you replace this with nitride layer, then you can isolate those cells by its property. Because the insulator, if you store electrons here, those electrons will not go to the next one. But those electrons are localized, trapped. So that's the innovation industry took. That, for example, Intel and Micron, they started with 3D floating gate, but now they're all in charge trap. Every company is now in charge trap. Okay, so that's the another innovation for increasing the number of layers, because this will give you relaxed aspect ratio. You can have a wider diameter for a given height. So that's all I wanted to talk about process challenges. Now, in a couple of minutes, we'll talk about some of those device physics of 3D NAND, and that's where your homework 5 will be coming in. Okay, process, we don't have much homework, but on device physics, we can show some equations and you can calculate some of those problems. So let's look at how those 2D and 3D cell looks like. So this was your 2D NAND cell, right? We have homework 3 on this, right? We solved homework problems using flash memory cell. It is a floating gate. When there is no charge, it is erase cell. When it was charge is there, you have program cell, logic 0, right? It was a planar gate. Gate was planar, single crystalline silicon channel, because 2D cells are made on crystalline wafer. That's why channel is crystalline, good quality. So inversion mode, isolated floating gate, and channel fast process. So you start with the channel, you start with the wafer. Whereas if you look at 3D, all are very different. Instead of planar gate, it is all around gate. Gate all around, right? This green layer is a gate, control gate. And we saw it, right? Why? Because of this process, the way it is grown. Instead of single crystalline silicon, it is polysilicon, which is bad. So tick and cross, right? Tick means it is a good thing. From 2D to 3D, all these changes are revolutionary change, not evolutionary. Evolutionary means you make 3 nanometer to 2 nanometer. Small change is evolution. But these are all revolutionary change, right? Instead of making planar gate, you make it gate all around. Instead of making single crystal silicon, you are making polysilicrystalline silicon. And this is a negative. Why gate all around is positive thing? Why going from planar to all around is a good thing?
Store more electrons.
One is more electron, another is more control. It's control gate, right? It should control this channel. Otherwise there will be leak. You want to turn off the transistor. If gate has less control on the channel, you cannot turn it off. Current will flow, right? So having gate all around is always a good thing for MOSFET. Even in logic, all the time, all the logic MOSFET like FinFET and all those things came to increase the gate control. Here, automatically it came about because of the process. Okay, so from planar gate to all around is a good thing, but every other thing is negative actually. Because single crystal will have higher mobility, here polysilicon will have less mobility. From inversion mode channel to junctionless channel, right? Here you can dope, for example, source and drain, highly doped, right? Source and drain, you talked about when you talk about MOSFET. In this 3D NAND, how can you dope? You're growing, right? It has to be undoped channel. So those regions are not doped. That means they will have higher resistance and they will cause lowering in the current. Okay, so this is another junctionless channel is a negative thing. Then isolated floating gate, which is a good thing 2D because charge will not share with another cell. But here it is a continuous charge trap layer. Charge trap layer is continuous sharing between two cells, right? So if you program one cell heavily, another cell is erased, some electrons can go there. Of course, it will take some time, and this is the issue. We'll talk about that as well. And then it's a channel fast process, right? Your channel is made fast, and here the channel last process. This is also disadvantage because sometimes you have less temperature budget. When something is last, you cannot heat it up long. Here channel is fast, so that means you make crystalline channel with a high temperature, for example, when you buy a wafer. Okay, let's look at one by one. So gate all around, why it is a good thing. So you have to look at the geometry or electric field. Electric field depends on the curvature. If you have a strong curvature or very narrow radius, your electric field will increase for a given voltage, right? So this is the very fundamental if you look at Gauss law and others, right? When you have high school physics, for example, right? If you have a planar gate, electric field is constant. But if you have a curvature, electric field will intensify. And that is what we need in NAND, because in NAND, your programming, erasing happens through electric field. It's all electric field driven tunneling process. So if you can intensify electric field because of curvature, which is a good thing. And why do you want more field? In the tunnel oxide. In the tunnel oxide will have more tunneling. Blocking oxide, you want more field or less field? Less field. Your blocking oxide should prevent tunneling. And this automatically happens here because your outer diameter is a blocking oxide. Your inner diameter is your tunnel oxide. So inner diameter will have higher field, outer diameter will have less field for a given voltage, right? So instead of capacitance ratio, it automatically you get this. And that will be a homework problem, so you need to solve that how much benefit you get. Suppose your thickness is same. Suppose, so think about like this. You have a planar gate like this, where you have blocking oxide and tunnel oxide, both are 8 nanometer. What is your coupling ratio? Coupling ratio, you remember coupling ratio should be as high as possible because coupling ratio decides you can lower your electric field, right? So coupling ratio alpha, right? If you have, so this is your gate step, floating gate, blocking oxide, tunnel oxide, and then your MOSFET. We talked about if you give VCG, most of the voltage should come in. So you can think about two capacitors in series, C box, C box. I hope you read all those things, right, in solving for homework. VCG, VFG. VFG should be as high as possible, and that's where this coupling ratio comes in. So VFG is VCG. Floating gate voltage is alpha times CH. If both these capacitors are same, coupling ratio will be half, right? But in this case, it will not be the case. In 3D NAND, if both these oxides are saying? What do you think? Coupling ratio will be half, more than half, less than half? It will be more than half, right? Because tunnel oxide will be much more having higher field and higher capacitance. Okay, so this is the reason. You can see it, your electric field. So this dashed line is for planar MOSFET. Electric field is same, right, in both the oxides. Electric field is not position dependent because it's a planar. But the moment you go in the curvature or cylindrical domain, your tunnel oxide electric field is fundamentally much higher than the blocking oxide electric field. And this is precisely needed because you want tunnel oxide field should be high for a given voltage. Blocking oxide should be less because blocking oxide should prevent back tunneling. So geometry helps here. And you can calculate the field enhancement factor because of the geometry and all. So all those things are good. So these are the papers from where these plots are taken. But the bottom line here is making things cylindrical, right? Or having smaller hole diameter means more curvature. More curvature means small r means higher electric field. And that will cause reduction in programming voltage. You don't need say 20 volt, maybe 18 volt is good enough. So that was one advantage coming from 2D to 3D. The other advantage, so this is the only advantage actually. After that, all are disadvantage going from 2D to 3D. And that's why industry took some time, right? 2007 idea was proposed. There was a paper written. But 2014, after 7 years, first product was launched to solve all those problems. Okay, so let's look at them one by one. So polysilicon, right, will have a lot of grains, less mobility, and that will cause you fluctuation in threshold voltage. Or your threshold voltage distribution, right, will be much wider. Earlier it was crystalline silicon. Between one cell to another cell, less variability. Now with polysilicon, your variability was much larger, right? Because polysilicon, you can think about doping. One cell is highly doped, another cell is lessly doped. So you fabricate all the cell identically, but because of this polysilicon grains and all, you will see a lot of variability from one cell to another cell. How industry solved this problem? So they use this one. So at the beginning, right, in 2007 paper, they used polysilicon in the entire cylinder. Entire cylinder was filled with polysilicon. That means more variability. What they did, they filled the cylinder with oxides. So this pink area is basically oxide area. So now instead of more polysilicon, you have less polysilicon, right? So polysilicon is used only for current conduction. Everything else is dielectric filler. With that, they minimize the variability, right? If you look at the diagram, so this was the variability, sigma. Y-axis is the probability, axis is the VT. This was the wide variability from minus 0.5 to plus 1, 1.5 volt variation. If you don't do this, if you just fill it up with oxide filler, your distribution becomes much tighter. So those are very, I'll say intuitive or more like innovation, right? Cute innovation industry came up with. Very small change. Instead of filling the entire memory hole with polysilicon, they just filled on the surface and filled it with dielectric filler, which is oxide. And most of the 3D NAND is now made in this way. And that way you control the thickness, right? By geometrically, you minimize the variability. Why variability is a problem for memory? Because you cannot pack more bits, right? Because you have to make your distribution as tight as possible. If your starting variability is large, it's very harder to tighten them later. So if you start with a less variability, you can pack more bits. So that's why it is important. Okay, so junctionless versus junction process, right? So in 3D NAND, because you don't have a source and drain between two cells, right? So now what they rely on is a fringing field. So you give 6 volt, some fringing field will come in, and that's how you invert those channels. So this fringing field is a problem, right? Because that will, so your bottleneck is now in those area which is sitting between two cells. Because you can control this conductivity of this region by this voltage, whatever you put on the word line. Those green things are word line. This red region is your polysilicon. So you can change the conductivity of this channel, right, through this voltage on the word line. But what about this intermediate region? So that's where you need to rely on the polysilicon, is this fringing field, and that will reduce your conductivity of the channel. So this is one of the paper that as number of layers are growing, this lowering in the current will take place, because you will have on current, which is bit line voltage divided by total resistance. Now resistance will increase with number of layers because of those interlayer region. With interlayer resistivity, you cannot control much. Okay, so that's the another limitation of having undoped source and drain. Isolated versus continuous charge trap layer, right? What is the, so any question? I'm going a little bit fast because I have 4 or 5 minutes. But yeah, slides will be up. You can see this is just conceptual understanding that how on current will change with number of layers if every cell or every interlayer resistance is given by R on. Okay, so in floating gate, the only way charge can lose is through tunnel oxide tunneling. But in charge trap layer, you have now extra path for charge loss. In floating gate, right, electron cannot go this way, electron cannot go this way, or lateral migration is not possible. Only vertically you can lose. But in charge trap 3D NAND, lateral migration, vertical migration, both are possible. So data retention, which is the critical for non-volatile memory, will be poor for 3D NAND. With 3D NAND, because of charge trap layer, charge will diffuse over time. Yes, it is slow because it is a nitride layer, but still there will be diffusion with time. So that's another problem for 3D NAND, data retention issues, right? Or extra path for charge loss. Question, anything so far? Yeah, so I'll summarize. This is the last slide. So one is something called revolutionary technology or revolutionary innovation and evolutionary innovation. In industry, most of the time it is evolutionary. From one technology node to another technology node, you change something, you make it happen, and then move on, right, for next 2 years. But 2D to 3D was really a revolutionary change because you changed fundamentally a lot of things, right? You changed from crystalline silicon to polysilicon, significant change. You changed from floating gate to charge trapping there because for scalability. Everything is driven by scalability. You want to scale or you want to increase more and more layers. You go from planar gate to double gate all around. This is the only positive. Everything else is negative. You go from inversion mode to junction-less channel, right? Or doping, undoped channel. You go from horizontal channel to the vertical channel. You go from gate last to gate fast. So these are all changes happened, and that's how 3D NAND is now the state of the art or the main technology for non-volatile storage. I'll stop it here, and maybe in the next class we'll continue the discussion. Yeah, thank you.
I have a question about the CVDs. When they do that, is it depositing on like the wall?
So to grow from outside to
From outside in? Okay.
Yeah.
So I was wondering if they were growing from the bottom up, like at the bottom of the channel from the substrate up.
Yeah.
Because I thought if you did it that way, it would take on the crystalline structure of the substrate.
Yes.
Right, but
They go bottom up. No, I mean this.
well, for the channel.
For making this hole top down, but for growing they go bottom up.
Right. For like the word line and the oxide layers, right? But for the channel,
Yeah.
it is to the side of the wall.
Yes.
Okay. Okay.
So you deposit all those layers one by one.
So it does like deposition, like goes, it sticks to the walls,
Stick
and then you do a different layer.
yeah, it's more like conformal deposition. Conformal.
Okay.
Conformal.
Yeah.
Yeah.
Okay. So I thought when I was looking at like making like LEDs and things like that,
Uh-huh.
they chose different crystals to grow on top of, so that the what was grown would take on the crystal structure similar to below.
Okay.
I didn't know if that was. I was just asking if that was a.
Because that is very precise, right? There, any interface defects will cause recombination.
Yeah.
For LED, right, recombination is a bad thing. Any recombination will minimize your, any non-radiative recombination. The defect-mediated recombinations are heat, non-radiative.
Right.
Band-to-band recombination is more like radiative. There are two types of recombination process. So that's why they want to minimize defects.
Yeah.
But here it is not that critical because your speed and all are not nanosecond range.
That's okay.
So that's where you got saved. But yeah, in terms of quality, not good.
Yeah, I was just curious if there was like, if that was how they did it.
Yeah. So I think the whole creation is from the top.
Right.
I think the growth, I think somehow the switch lines they can also play some role.